All right, hello all. Welcome to the final video for section 1.3. Continuing on with kind of our themes of rates of change, but using them to analyze some different aspects of a function. Okay. All right, so first let's talk about increasing or decreasing. So we say that a function is increasing on an interval if the function values, meaning the outputs, increase as the inputs increase. Okay, and then it's got a very formal definition there, which I'll come back to, but important piece here, the average rate of change of an increasing function or over an interval where the function is increasing will be positive. Okay, so when you calculate a rate of change over a particular part of a function or a graph, if you get a positive number, that means the function is increasing. So let's also look at what this means visually. This is where I'll use the other part of the definition there, so I'm going to draw this down below. So let's say we have a graph that will look, say, something like this. And they say if we're looking at inputs where b is greater than a, well, that means the value b, whoops, not using that though, the value b out here will be larger than the value a back here. And we also have that f of b is greater than f of a, meaning here we'd have, darn it, wrong thing again, f of b up here and f of a down here, because f of b is greater than f of a. Well, notice if I connect the dots in this graph, so here, which is a f of a, to here, which is b f of b, notice that from left to right the graph is going up. Okay, so that's one of the surefire ways to identify whether a function is increasing over an interval, is to look and see if from left to right is the function going up or down. If it's going up, then it's increasing. On the flip side, a function is decreasing if the function values decrease as the inputs increase. And I'll come back to this next part, which is the formal definition. But again, I want you to focus on this last part, which says the average rate of change of a decreasing function is negative. So if you calculate the average rate of change over an interval and get a negative number, that means your function is decreasing. And to connect this now to the other part of the definition, drawing a picture here. So here again, it says that we're going to have b greater than a. So b is still bigger than the value of a. But in this case now, we have that f of b is less than f of a. So that would be something where f of b would be down here, f of a would be up here. If we now connect the dots between a, f of a, and b, f of b, notice that the graph now goes down from left to right. So if we have a graph of a function and it's going down from left to right, or over an interval it's going down, that means the function is decreasing on that interval. Okay? Now, increasing and decreasing are helpful to help us identify what are called local extrema on the graph. So this formal definition here says that a function is, a point where a function changes from increasing to decreasing is a local max. A point where a function changes from decreasing to increasing is called a local min. Now, those are really technical definitions. But what you might already be more familiar with these is in terms of points that are higher or lower than others on the graph. So these ones that I'm highlighting, this one here, and this one here. Those are all examples of local mins and local maxes because there's that word local there. So for the points around them, the points that are local to them, they're either higher or lower than those. So this first one here, okay, notice. So that's what we call a local min. Okay, this one here is higher than the other points around it, so that's a local max. Okay, and then this one here is lower than all the ones around it, so that again is a local min. Now notice that last one I highlighted there, this one, that's not the lowest point on the graph. It's just lower than the ones around it, which is what makes it a local min. Okay. This one here is actually the lowest point on the graph, so we have another name we can call that. We can actually call that a global min, or absolute min is another way you see it referenced, okay? Which hopefully, again, that makes sense that we're global or absolute because it's absolutely the lowest point on the graph, okay? And this function actually does not have an absolute max or global max because if you'll notice here, the graph goes up forever and ever to the left and the right, so there's no highest point, okay? And local mins and local maxes, the general term for them altogether are local extrema. Now, I do want to look at these in terms of their formal definitions about increasing and decreasing. So notice to the left of this point, x equals 1 here. Okay, the graph is going down from left to right. So there we see that it's decreasing. But then to the right of it, the graph is going up from left to right. So it goes from decreasing to increasing. So that matches what we have here. So that's why that is a local min. Notice for the value at x equals 3, to the left of it there, it is increasing. To the right, the graph goes down from left to right, so it's decreasing. So we see this is going from increasing to decreasing, which follows this top definition here, which shows us why that's a local max. And then for the last point there, see that to the left of it, where x equals 4, we have that it is decreasing, and then to the right of it, it's increasing, so it goes from decreasing to increasing, which again fits the second definition, so that's why that is a local min. Okay. One last thing about local extrema, at those points, the graph is neither increasing or decreasing because that's where it changes from increasing to decreasing or decreasing to increasing. We cannot say that it is either increasing or decreasing there, so it's neither at those points. All right. Let's look now at something called concavity and get really technical here for a second. So notice on this left-hand graph here, they've got some points to the point 0, 0, 1, 5, 2, 7.1, 3, 8.7, 4, 10. And notice they calculated the rate of change between each of those points. And notice that the rate of change is decreasing. Okay, and you can see that here where there's a large increase followed by a small increase. So even though it's increasing over all those intervals, the amount of increase is getting smaller. And notice that part of what's going on with the graph then is it's got this curvature that's kind of facing down, right? Like if that was like a face or a bowl or something like that, it would be facing down. Notice for this other graph on the right here, okay, if we look at similar points, and I meant to do that like this, okay, and they again calculated the rate of change between each of those points. Notice that that rate of change is increasing now. Okay, and you can see that it goes from a smaller increase to a larger increase. And notice that for the curvature of the graph there then, what that's got is it's kind of got this curvature that is facing up, right? So it's almost like a bowl that's facing up or part of a smile or something like that. Okay, well, these are examples of concave down and concave up. So the one on the left here, this is what we call concave down. And that's because the rate of change is decreasing, but really what we're focused on here is that the curvature is facing down. And this one here is concave up. Okay, because it's got that curvature facing up now, or the cup is kind of facing up. All right, so our technical definitions of that, we say that a function is concave up if the rate of change is increasing, but again, I like to think of it as the bowl, or one way a student used to say it is up like a cup, so it's like a cup facing up. Concave down is that the rate of change is decreasing, so that's like the left graph up there. And another way to think about that is down like a frown, right? This part of this graph, whoops, sorry about that. This graph kind of looks like a frown, so that's down like a frown. And just like with local extrema, where they were points where the function changed from increasing to decreasing, we can also have points where the function changes from concave up to concave down or vice versa. We call that an inflection point. And one thing about identifying an inflection point is it's usually halfway between a local min and a local max. All right, and so here's some different examples of concave up and concave down. So notice on the top here we have an increasing function, but it's concave down because the curvature is facing down. The second one is also concave down, but notice now it's a decreasing function. And then here below we have concave up example. So here's a function that's increasing but concave up, and then one that is decreasing but also concave up. All right, so we're going to put all this together now and do some identifications of places where the function is increasing, decreasing, where local extrema are, inflection points, and then concave up and concave down. All right, so let's start with increasing and decreasing. And I'm going to start by highlighting points on this function where it's increasing. So it looks like starting here. Okay, and still not there. Tampoco. Here we go. All right, so that part where I just highlighted, that is a place where the function is increasing. And here it's also increasing. Okay. And we're going to identify those intervals over which it's increasing. Now, first of all, I should point out that there should be arrows at the end of this graph, so it is continuing forever and ever in each direction. And when we go to identify the intervals of increasing, okay, we're going to do it based on the input values that are covered by those intervals. We're going to write this in interval notation. So first of all, notice for this first piece here, okay, well, the function is continuing on and on to the left. So it looks like the place where it starts increasing is going to be way out here to the left, which would be an input value at negative infinity. And then it increases from negative infinity all the way up to -8, -7, -6, -5, -4, -3, and then it looks like it stops increasing there at the value -2. Right? And in fact, that -2 looks like a local extrema. Remember, I said that it's neither increasing or decreasing there, so we put a parenthesis there. So we see that the function is increasing from negative infinity to -2. And again, the reason for that is we see the graph is going up, sloping up that whole way. And then there's a pause and something else happens and the graph looks like it decreases. And then we union that with another interval where it's increasing that starts right here, it looks like, at 4, but not including 4, because that's a place where it changes from increasing to decreasing. And then it goes further to the right. So it looks like our interval for increasing would also include infinity. So our increasing interval will be negative infinity to -2, union 4 to infinity. Okay, and that's because those are those two pieces of the graph there where it's increasing. All right, let's now look at decreasing. So decreasing, remember, is where the function is going down from left to right. And it looks like here where that is happening is from the value -2, or on the input value -2 down to 4 there. We see the function goes down. Okay, so our interval notation for our decreasing would be -2, 4. And remember the points -2 and 4 is where it changes from increasing to decreasing or decreasing to increasing. So it's neither at each of those points. So put parentheses around those. So our decreasing interval then is parenthesis -2, 4. All right, so that's the first part. We were asked to identify intervals over which the function is increasing or decreasing. Next, identify local extrema, which means we want to find mins and maxes. Okay, And recall that these are points that are higher or lower than the ones around them. So first of all, I see that here at -2, looks like we have a point that is above all the others. So I can say that there's a, sorry, not a min, that would be a max, local max at x equals -2. And I could do the coordinates there, which are -2, 0, but I'm just going to identify the input value. For a local min, well, that seems to happen here at this valley. And that seems to be at the value x equals 4. Okay. So this would be where our local mins and local maxes are. And just to point out here, this function only had one of each, but it does not have to only have one of each. It could have multiple, like 2, 3, 4, or more of each of those. All right. The next thing then, based on the instructions for number 3, is to identify all inflection points. Okay, an inflection point is where the graph changes from from concave up to concave down, or concave down to concave up. Now, as I mentioned, it's sometimes hard just looking at a graph to figure out where the inflection point is. So an easier way to find it is to look halfway between mins and maxes. So notice, again, there was a local max at -2, local min at 4. Halfway between those would be, I think, at x equals 1, right? Yes. And so that will be our inflection point at x equals 1, because it's halfway between those two. And hopefully you notice, and I'm going to go ahead and clear all this out. So again, I said that the inflection point is at x equals 1. Hopefully you notice, if you look to the left of that point, look at the concavity, it kind of looks like it's concave down. And is that different than the concavity to the right of that point? Well, yes, it looks like that is concave up, right? So it's up like a cup. So we can identify this stuff then. So for concave down, I'm going to say CD. The intervals, and again, we're talking about the intervals of the inputs where that happens. So concave down is to the left, the stuff highlighted in orange. It looks like that starts at -infinity, so way down over here somewhere. And it stays concave down all the way to that point 1. And then because that point 1 is a point where it changes from concave down to concave up, we don't actually include that in the interval of concave down. So we put a parenthesis there. So our interval of concave down is -infinity, 1. All right, the concave up then. Well, that's going to be starting at 1 and then going all the way to the right forever, so to +infinity. So put parentheses then around each of those, because at 1, that's where it's changing from concave down to concave up, so that's not included. And then it goes on to infinity off to the right. Okay? Whew, we made it. Good job. So that's the end of section 1.3. Thank you for your attention, and I'll see you in the next video.